Alright, hello and welcome back. Let's finish up these slides and then maybe start some new ones. So this is game theory we were talking about. We ended up talking last about the prisoner's dilemma, which was a very fun concept, and we learned about Nash equilibrium, and the Nash equilibrium for the prisoner's dilemma is a case that seems paradoxical. Like they have to both confess, which is odd, but it actually makes sense. So that's that. Talked about this last time. And now let's talk about the final, because that's coming up. Maybe that should be a proper noun. Alright, so I'm going to release a module on Canvas. It's going to be under week 18, take the final and you are free. So final info, and then there's also some extra credit that I'm going to talk about. The final exam will appear there as well, like it did for the midterm. So that's the idea. So go here. I'm going to eventually release this and take a look, but here is the idea. So finals at this college are supposed to be an hour and 50 minutes long. Okay, if you go and look at the schedule, like if a class had a time, it would be an hour and 50-minute exam. But I will give you 2 hours. Okay, so I'll give you 120 minutes to take the exam once you click start. And as I said at the very beginning of the semester, it's going to happen on the Tuesday. So I'm going to release it on the Tuesday of finals week, and then I'll also give you some time on the Wednesday as well. So if we go all the way down to December, the 8th is the Tuesday, and then the 9th is the Wednesday. Okay? So in between 12 p.m. on the 8th, the Tuesday, and 2 p.m. on the 9th, which is the Wednesday, you can take the exam, but you'll have 2 hours to do it. So if you want your full time, you better start at noon on the 9th. Okay? That's the idea. Okay, so yeah, I'm going to make the test. Like, I'm not going to give you 2 hours and then give you 10 extra minutes of extra questions. I'm going to pretend that this is an hour and 50-minute test, but I'll just give you 10 minutes of extra time because maybe your internet's slow or something. So here are the topics. Again, we're going to give an essay, so prepare to write an essay with at least about 250 words. There will be a word limit this time. I have learned better. And then also there will be some coding questions to just go over all the programming stuff that we've been talking about. Finally, I can ask you some coding questions. So prepare to write some code, okay? You're going to paste it into a Canvas text box, just like you would for an essay. But just be ready for that, okay? So maybe have Python open when you begin the exam. And to study for this, I encourage you to just go over the programming assignments, make sure you understand how they all work, and also the in-class example programs that I've been giving. So I'll use those coupled with the things that I have talked about to come up with the questions. And the essay, it takes a while to write 250 words, I know, so that will give you the majority of your points. At least 51% of the exam will go towards that essay. And yeah, it's open book and open notes, but don't talk to somebody while you're taking the test, as usual. That's all I got for you. So that will be the final. And yeah, please ask me any questions. Yell at me if you have any see any issues or anything like that. Also, one last extra credit opportunity. Take advantage of it if you would like. Make a Python review video for yourselves now that this will be on the exam, and then also for my future students. So again, it's going to be 5% extra credit, and yeah, just turn it in by the last day of instruction. That's the idea. And yeah, as last time, just make a video that reviews Python stuff. Go put it up on YouTube or somewhere, or you can upload it as well, whatever you'd like. But this is a discussion, so your peers are going to see your submission, which is perfect. And they will love you forever because you're giving them stuff to study with. So as before, as for the Scratch example, extra credit, you're going to essentially make a mini lecture, right? So you're going to give a bunch of examples that explain some topics and try and make them a bit challenging, so that if anybody can master what you're teaching, then surely they can do well on the exam when it's timed and not as hard. Okay, so give some examples that are kind of hard, not too hard, but not super easy, and don't just copy something that I did in class. Okay, That's all. So it should be unlike anything mentioned in class or the assignments, but you can use those as like guidelines. All right, you'll have to teach the same concepts. Like, don't teach a random Python concept that I haven't talked about. But when you make your examples, just don't reuse the ones that I used. That's all. Okay, and yeah, just pretend you're me giving a lecture and explain everything you're talking about. Demonstrate them as best you can. And yeah, same time limit as before. If you want at least 2.5% extra credit, your video should be at least 15 minutes. And if you want 5% extra credit, your video should be at least 30 minutes. Okay, so that is the idea. And I think that's all I have to say about that. So consider doing the extra credit if you would like. Okay, so let's go back to game theory and let us discuss cake cutting. So we've been talking about non-cooperative games so far. The Prisoner's Dilemma is a non-cooperative game. I can't tell if this one is a cooperative game or not, because it has some elements of cooperation, but at the same time, that the cooperation that you're doing in this game that I'm about to explain is kind of forced upon you. So here's the game. You probably played it with your siblings, if you have siblings. So the idea is one of you cuts the cake, and then the other chooses which piece to get. So that's like super fair. Maybe your parents made you do that so that you weren't like stealing cake for yourself. But this is a game. We can think about it as a game. And what is the optimal strategy for this game? Surely if you played it, you have learned the strategy. So if you have a giant cake and a sibling nearby, if you cut the cake like this, like here's one piece here, and then here's the other piece, which is the rest of the cake, which one do you think your sibling is going to pick? Okay, they're going to pick the big one. So the optimal strategy is, of course, to cut it perfectly in half. And now you can see why it's hard to determine whether or not this is a cooperative game or not. You are forced to cut it in half because if you want any cake at all, you're going to make this fair. Because you know that your opponent or your sibling is going to want to choose the slice that is bigger. Okay? So this is how you make it fair. And this seems to be the one optimal strategy, unless maybe your sibling is full or something. So that's cake cutting, and it's a good lead-in to this next topic that is called Pareto Optimality. So what we have done in cake cutting is we've allocated resources. It's just a fancy word for that. So we have some resources, a cake, and we have allocated them. We've cut it, okay? A slice, okay? And a resource allocation, so a cutting of the cake, is called Pareto Optimal when if you were to change the allocation, if you change the allocation for somebody, maybe it's a game with multiple people, it always leaves somebody worse off. Okay? That's the key. If you were to change the way you cut the cake, somebody would be worse off. That means that your resource allocation was Pareto Optimal. Okay, and so this is really nice and fair, and I think that John Stuart Mill would have a lot of fun with this concept because it's kind of utilitarian. Like it's always looking for the good for as many people as possible. Okay, it's averaging out the good for everyone. So let's talk about some Pareto Optimal allocations for cake cutting. So remember, what kinds of cake cuts would make it so that if you were to change the cut, somebody would be worse off? Dun dun dun. So let's figure this out. Let's go back to our optimal cake cut. Boop. Cut it straight in half. You get this one, your sibling gets that one, everybody's happy, right? There's an equal number of cherries and everything. It's all beautiful. Well, if you were to change the way you cut this cake, like maybe you gave this sliver to one side, like you moved this one over there, and so now there's a slightly less amount of cake for somebody. Ooh, that left somebody worse off. You see that? It's going to leave you worse off because your sibling's going to pick the bigger half, but nonetheless, it left somebody worse off. So the optimal one, the cut straight down the middle, cutting the cake in half, is Pareto Optimal. Now, this is an interesting example because let's go back to our very unfair example as well. Let's say this was our allocation. Tiny little slice for ending up you, and then the bigger slice for your sibling. Well, if you were to change this allocation to maybe give a little bit more for yourself, like here's like a little bit less, and here's a little bit more for yourself. Notice that, well, because your sibling's going to pick this side, you're going to gain a little bit. So that leaves you off, that makes it better for you, but it also leaves your sibling worse off. You see how they got less cake in that case? So, in fact, every allocation for cake cutting is Pareto Optimal. Which is kind of weird to think about, but if we just follow the definition, it is the case. A resource allocation is Pareto Optimal. When you change it, it leaves somebody worse off. If you change the way you cut the cake, somebody's getting less. Somebody might get more, but somebody's getting less. You see that? It's interesting. So that is a weird case of Pareto Optimality. And actually, an even weirder case goes back to the prisoner's dilemma. Oops, sorry for the weird edit here. I had a small mistake in my write-up here, but I want to explain Pareto Optimality from the point of view of the prisoner's dilemma problem now. For that issue, it just so happens that the Nash equilibrium, which is everybody confesses, right? If we scroll back on up here, everybody confesses that is the Nash equilibrium. That's what everybody's going to want to do. That is the optimal strategy, in a sense. That is a non-Pareto optimal outcome, in fact, because there are ways. There's a better outcome, right, for both prisoners if they just didn't both confess. Neither of them did. They would both have less time in jail, right? So the Nash equilibrium is not Pareto optimal, and that helps to explain, I think, why this is so counterintuitive, this process. So that is Pareto Optimality in a nutshell. Okay, so hopefully your brain isn't too fried yet. Let's now move on to a new concept. Another truly cooperative game this time. So it's splitting a taxi ride. Or maybe we should update this to be like in the 2020s, this is maybe a Lyft or an Uber ride. So it's a cooperative game. So let's pretend we have two people, and in computer science, if you ever like have examples of actors, things, entities, people doing things, they like to give them, like, instead of person A and person B, they like to call them Alice and Bob because those start with A and B. Okay? And then you know if they have a third person, that name is going to start with C, which is hilarious. So that's the way that computer scientists like to roll. And so Alice and Bob, they share a taxi. And Alice just so happens to live on the way to Bob's house. So, like, here's where they currently both are, and here is Alice's house. And here is Bob's house. And Alice lives on the way to Bob. So now this is a weird game to play because of the way these fares are about to work. So because they're sharing a taxi, they want to split the bill somehow, and we need to figure out the best way, the optimal way to split that bill. And so let's talk about our options. So if Alice went and got a taxi by herself, she would pay $5 to get to her doorstep alone. Okay? If Bob got a taxi by himself, he'd have to pay $12. And apparently it's cheap to just stop the car for a split second and have Alice run out. So the fare for both of them together is the same as Bob's price. So it's still $12 if they both share a taxi. There's multiple seats in a taxi, of course. So if they both took it together, it's $12. So how in the world should they split the bill? Because, well, it should be cheaper for both of them, but they don't. It shouldn't be average, okay? So we shouldn't average the bill. 5 plus 12 is what? That's 19 divided by 2 is 9.5, yeah? So $9.50 if you average it, but that's way more than Alice would have ever paid, so she might as well go alone. And then, yeah, Bob's better off, but, I mean, what's the point? So let's figure out how we should do this. Alice should pay a bit less, yes, but not more. Definitely not $9.50, not the average of these two numbers. Because then Bob would, yes, pay less, but Alice would have to pay much more than she ever would have alone. So what's the fairest way to split this bill? And the way that we come up with this price is to compute what is known as the Shapley value. That will tell us the answer, and it's a fancy concept. I encourage you to look it up. But the idea, at a very high level, in a nutshell, is to think about all the permutations of, they're playing the who pays first, who pays the remaining bill in what order game. And then we take the average of all those cases. So it's weird that this works. I don't fully understand it enough to be confident to explain it. But let me show you it working, and it comes up with a value that I think you would agree is okay. All right, so the idea is we consider all the permutations of who's paying the bill first. So there's two orders. Alice could pay the bill first and then Bob, or Bob could pay the bill first and then Alice pays what's left. So this is the idea. So Alice pays first in this scenario, and then the second person pays what's left, pays remaining bill. So let's figure out what they're going to pay. So Alice, Bob, in each of these scenarios. So there's this scenario and that one. So four total. So if Alice pays first, that means she's paying the rest of the bill. That would have summed up to her final fare. So she's going to pay $5. Okay, so Alice would pay $5 with this permutation, where she pays as much as she should, and then Bob pays the rest, the remaining bill. Okay, and then if we were to follow along with this order still, Bob would be paying the remaining part of the $12, because that's the total still, because they're both taking the same taxi, right? Which would end up being, $7 for Bob? Yeah? So Bob will pay $7 in that case, and Alice would pay $5. So obviously this is not optimal, because Bob's paying less, but Alice is paying the same amount, but we're about to average these in a second. Okay, the other option is if Bob pays as much as he needs to pay first, and then Alice pays the remaining bill. So if Bob pays first, he's paying the full $12, because that's how much it costs to get to his house. And then Alice would have paid $0 in this case. She's paying the remaining bill, but Bob already paid the full bill. See that? My little dollar signs are not very aligned. Let me fix that. 12, and Alice would pay 0. And so the idea now is we take the average. We take the average of what's left, and don't worry, I'm not going to test you on this. It's just really cool that it comes up with the right thing. And this is the way you do it if you ever share a lift with somebody. This is how much you ask them to Venmo you. Okay, so the average now for Alice over these two permutations. Obviously, if there's 3 people, there'll be 6 permutations. You know your math. The average is going to be 250. So that is actually the optimal amount that Alice should pay. That's the fair amount in this cooperative game. And then Bob pays the... Oh, sorry, this is, first of all, 17 over 2. How dare I? Probably yelling at me through the screen this whole time. This average is 17 over 2, which is not 950. I am so sorry. You can math, but I cannot. So it's 850, right? So still too much for Alice to pay. Hey. My argument stands. And in fact, now we're going to calculate 950 because that's the average of what Bob would pay in these situations. So Bob would end up paying 950 total. And so notice that, yes, this is going to sum up to the final $12, and Alice is paying less, and Bob is paying less. Okay? And it's proportional, which is wonderful. So this is a fair taxi ride, and it is an example of a cooperative game because Alice and Bob are working together to pay a smaller fare. Okay? They would have paid more if they went alone. Okay, so one last example, and it's a fun one. I encourage you to watch this video. There's a man that explains it much better than I can, I am sure, but I will give you the gist of it and still make it fun. So, Tic Tac Toe is a game, of course, obviously, and if you were a computer, like, how would you win? There's a way. There's a way called Minimax, which is a fun little word, and this is a strategy. It's a type of strategy, okay? Or it's a type of search to find a strategy. Okay, so imagine that we were at this point in the game, and we're X, okay, because we want to win. We are X. So how do we figure out the best move to play? Okay, obviously you know that the best move is going to be this one, but how can we come up with that? Like, given the game board, no matter what, how do we know? The idea is we can simulate the rest of the game. Okay? We're going to play every option. We're going to just play it out for the rest of the entire game, and we can do this because this is a small little game board. It's very hard to do for chess, of course, and it's even harder to do for Go. We've talked about this. Okay, so the idea behind Minimax is when it's our turn, we make the move that maximizes our chance. It's kind of backwards. That maximizes our chance of winning. Okay, that is key. And then when it's our opponent's turn, because we're simulating the rest of the game, it's going to be our turn for a little bit, and then it's going to be the opponent's turn. We're going to keep on switching spots. When it's the opponent's turn and we're simulating the game, we're going to assume that they're going to make the best move for them, which minimizes our chance of winning. Okay? So we're going to assume that the player is going to make the best move. Okay? So the idea is, if we assume we have the best possible opponent, we can play the game out, and we can see how well we do in each case. Like, if we put the X here, how well do we do? If we were to instead put the X here, how well do we do? Then the O could go here or here. Just find out all the different ways we could play this game. And remember that our opponent is going to want to win as well. Okay, so there's like a give and take between the opponent minimizing our chances and us trying to maximize our chances. And so that's why we call it Minimax or Minimax. Okay, so let us simulate the rest of the game now. So let's take our game board. It's XOO. I can kind of see it, so this is perfect. So here's our game board way up here. I'm going to try and draw it small. XOO blank O blank blank X X. And here is what's about to happen. So I'm going to make some moves. So this is still way too big probably. So let me prepare to draw way too many game boards. There we go. Let's move this up as well. So what's about to happen is we're going to play the game. So it's our move right now, okay? Let's pretend that it's our move, and we want to figure out which way to play this game. So the idea is, okay, here's our first option. We have three different options to play our X. There, there, or there. So let's pretend that we try all of them. We're going to simulate the entire game, remember. So let's say this one is going there. So X, O, O, that's going here. Okay, that's one move. Then the other move is if we went here or here. Those are the other two moves. You know what I should be doing is copying this entire board. There we go. There we go. So alternatively, I could go here, or I could go here. All right. And we know this is eventually the move that we want. Don't worry, we'll get there. But this is how you use Minimax. And now it's our opponent's turn. And so, okay, from this point of view, they have two options. Let's try all those options. Boop. Boop. Let's try and make this a little bit. Oh no. Try and put this way over here maybe. So the opponent from here has two options. They could go either put an O here or an O here. And ooh, they win in one of those. Interesting, interesting. So we could actually stop the search in that case. And then the opponent could also have two options here. So they have two open spots. So here's what they could do there. The O could have gone right here, or it could have gone right here. Okay, you see that? And then, finally, in this last case, there's actually nothing to do because the game's already over. Okay? So, here's how we do Minimax. We give a score. Give a score to each possibility. Okay? Higher scores to better possibilities. So for this one, for example, how many cases do we end up winning in? Something like that, but not quite. Let me not write it. So in this case, we won. Okay, so this is like, we can give that a score of +1. That's beautiful, because we won. Positive number. Whereas, way down here, there is an option for us losing. So the O wins. There's also, if we go down here even farther, we'd eventually find a way for us to win because we have this option. So this game board would give us a score of +1. This game board would give us a score of -1. We don't like that. And then the same with these. So for this one, this game board has been 1, so we'd give it a score of -1. And then for this one, because we are about to win, because we can go right here, in that case, we can give that a score of +1. And, okay, so now, how do you bring these scores back up, these possibility trees? The idea is, this was the opponent's turn. What they're going to do, remember, is to minimize our chance of winning. Aha. So the score for this one is, we know we're going to pretend that our opponent is going to minimize our chances of winning. Oops. Therefore, you know that they're always going to make the winning move for them. Aha. So that means the answer is the minimum of all of these, which is -1. -1 of a score for this whole example. Okay, and again, +1 or -1, the opponent's about to minimize their choices, so the score for this scenario should be -1. Okay, that's the idea. And then we're going to, because this is our move right now, which of these do we want to do? We've got to maximize our score. We're going to choose this one right here, okay? Because it maximizes our score. Okay? So for us, we maximize among all of these, and our opponent is minimizing over all of these. Min, and that is a max. Okay, that's a fun little example, I think. So that is Minimax with Tic Tac Toe, and that brings us to the end of these slides. So I hope you enjoyed them. A little bit of a taste of game theory, and let me go get ready because we have a few minutes left. Let's start on the next set of slides, and then we'll be out of here. All right, I'm back with new slides. The title of these slides is called Recursion and Beauty, and I am really excited to teach this to you. This is recursion is one of my favorite topics to teach. So let's get started. Recursion, it's a very interesting word. You might have heard it before, but in computer science, it means a very interesting thing. It's a type of solving a problem. Okay, so here are some examples of recursion, and the idea of recursion is you're going to solve a problem in terms of itself. Okay, so that's what recursion means. All right, so recursion means solving a problem in terms of itself. And the short answer is no, it is not circular reasoning to do that. For a reason I will say in a second. So here are a bunch of examples of real-life recursion, I guess. So maybe you've used these Russian stacking dolls before. Inside of the largest one is the second largest one, and inside of that one is the third largest one, and so on and so forth forever. And maybe if we were able to make smaller and smaller dolls, like we can keep this going forever, right? So that's a real-life example. These Towers of Hanoi, if you've heard of that, is a fancy game that you can play where you have to always move these little discs. The goal is to move this entire set of discs to this peg right here, using this one as like an intermediate peg. And the rules of the game, if you haven't heard before, is only the larger discs cannot go on top of the smaller discs. So you can't put the small disc down here, and then you have this one. You can't put the second one on top of it because it's bigger. So it would have to go here, for example. And so you'd have to think really hard about how to play this game. And it's in fact, you can play the game inside of itself to solve it. And then a nice example of recursion is like when you have like a Zoom window open and you're sharing your screen at the same time. So you can see your screen go on forever and ever and ever, or you're looking inside of two mirrors. That's an example of recursion. So in real life, but in recursion for mathematics or computer science, it's when you solve a problem in terms of itself. And it is not in fact circular reasoning to do that because of a certain condition on the recursion. So it's not in terms of itself, in terms of, well, it is in terms of itself, but it's in terms of smaller versions of itself. It's okay to do this because of this. That is the key. So the idea is, in computer science or mathematics, you find a problem, that seems to have the problem inside of itself. And I will give you an example. So you find a problem that has the problem inside of itself, and that is called a subproblem. And then you use the answer to that subproblem to solve the whole thing. And this is all probably very theoretical, even philosophical, and not making any sense at all, but that's okay. I'm going to give you an example. And I think I'm going to shift these around. So factorial, finding the factorial of a number is a recursive problem. Okay. I'm going to prove that to you. So let's find the factorial of the number 5. Do you remember how to do that? So I think if you just remember the definition, that okay, 5 factorial is 5 times 4 times 3 times 2 times 1, right? Okay, so because I'm claiming that this is a recursive problem, you have to find it inside of itself. Can you find a smaller factorial problem inside of this 5 factorial computation? Take a second to pause the video, see if you can figure it out. And I think, eventually, you will notice that right here, well, there's actually a few, but here is 4 factorial. Here's 3 factorial. Here's 2 factorial. And there's 1 factorial sitting right there. So I can find 4 different factorials inside of this one. Actually 5 if you include 0 factorial. We define that to be 1 in math. Well, that's beside the point. So yes, we can. It's 4 factorial. So that's super nice. And okay, how can we use 4 factorial to build up the final answer? Too many exclamation points. Thinks that that's the beginning of a sentence. So how can we use 4 factorial to build up the final answer of computing 5 factorial? So 4 factorial is all this. How do we get 5 factorial? Based on that? Well, just multiply by 5, right? Just multiply by 5. So now we know. So we get 5 factorial. So now we know the idea, and this actually generalizes, of course. To most positive numbers, I guess. Let me just say most numbers. How do you calculate n factorial? So if I was giving you n factorial, well, we notice that 5 factorial equals 5 times 4 factorial. With this pattern in mind, how do you calculate n factorial for any n? Just pretend, okay, it was 5. So it's, okay, if n was 5, I'm going to multiply it by n again. So n factorial is n times what? How do we go from 5 factorial to 4 factorial? It's just, all right, take n minus 1 and find the factorial of that. You see that? So that is the definition of factorial in terms of itself. Okay, this is called a recursive case. So we've just defined the factorial problem in terms of itself. Okay? And there is one last issue. That's the recursive case. And remember, it's smaller versions of itself. Because we got smaller, like it was 4 factorial, not 5 factorial. It was n minus 1 factorial, not n factorial. Eventually, like remember, what's about to happen if we keep following this rule? All right, yeah, 5 factorial, that's 5 times 4 factorial. Okay, but that is 4 times 3 factorial. Okay, given our rule, that's 3 times 2 factorial. Okay, given our rule, that's 2 times 1 factorial. okay, that one's 1 times 0 factorial. That's still technically correct and fine. And now we get into a problem. Okay, yeah, that's 0 times -1 factorial, yeah? And so on and so forth until the end of time. So you need a place for this to stop, okay? We want this to stop, okay? Eventually it's going to get to smaller and smaller factorial computations, and eventually it's going to become incorrect because we might get down to 0 even, and -1 factorial, which doesn't make any sense. So here's what we do. In addition to the recursive case, we need a way to stop the problem from continuing, from what's known as recursing forever. We need to stop it, okay? And a stopping condition is called a base case. So when do you immediately know the answer to factorial? Without having to do n-1 factorial. And the answer is, once you get down to either 0 or 1, pick which one, but let's just pretend that, okay, yeah, 1 factorial, that's just defined to be 1. We don't have to do any more factorials after that. It's just 1. And that'll stop it, because then right here it's like, oh yeah, that's 1, and I can build up the answer by multiplying. I hope that makes sense. So I'm going to give a lot of examples, don't worry. So this one's called the base case. Okay, this is the stopping condition to the recursion. All right, so you're now experts on how factorial works, and well, this is computation. This is performing a task, and you can actually program this. So let me get a setup for next time when we program this. So so let's call it like fact or something. And if we remember what's going on here, I'm going to call it def fact of n. And we got to do something in here. Remember our base case and our recursive case. Oh, sorry. 1 factorial equals 1. And our recursive case. We know that this all works because we tried it out for 5 factorial. And this got smaller. It's all going to work out. It's eventually going to hit the base case. We can write a program that does this. Okay? So functions themselves can be recursive. So what does it mean for a function to be recursive, to be defined in terms of smaller versions of itself? Well, that means that functions can call themselves. Which is the weirdest thing to think about, but it's gonna work. A recursive function can call itself. Okay? So inside of the definition of the fact function, we can put another call to the fact function, and it will go off and compute this answer and then use it in the rest of the code. Which is gonna blow your mind. I know it's a weird thing to think about, and it takes a while to sink in, but let me show you how we can program this very quickly, and then we'll actually program it next time. Okay, so a recursive function, it calls itself, which is the weirdest thing, but that's okay. So we need to figure out if we're in the base case or the recursive case. So if we're in the base case, if n happened to be 1, well, the final answer is just 1 in that case. We're trying to calculate the factorial of 1. So we'll return 1. Else, n was not 1, so maybe it's bigger. Technically, this won't work for negative numbers, but that's okay. Else, how do we do this? We need n-1 factorial. And we can actually get that by calling fact again. So fact n-1. Call that x or something. So we can actually compute that factorial right there. And all we have to do to get the final answer is multiply that by our n, and that's what we give back. Well, let me put it in front. N times x. And technically, I don't even need to save it in a variable. I could just say return n times fact n minus 1. So, isn't that the weirdest thing, first of all? And second of all, I hope that it's starting to slightly sink in. Because this is a smaller problem. It can go off and compute that eventually. It'll go all the way down to like 2 times 1 factorial, and it will compute this one using the base case, giving back 1. And then after that, you're home free, because it can just keep on multiplying by its ends. So next time we're going to program this, and I'm going to show you very, very slowly why it works. Okay? I promise it. Okay. So with that, I will now see you in the real programming lecture, but now these lectures are going to start like morphing into each other, because suddenly we're going to talk about coding in the normal non-programming lectures now, and so I'm going to be programming a bit there too. So I guess I will see you in the lecture that is usually about programming. How about that?